All right. Hello. Yeah, in this episode, we're going to do section 11.1.2, which is permutations and combinations. Those two things we're going to define in a little bit, but they are two different ways to count in certain situations. And we're going to see if we can figure out what the difference is between them, how to use them, when to use them, and how to use the calculator to help with that. So, our essential question is, what is the difference between a permutation and a combination, and when do I use them? Basically, what we just said. Our warm up, real quick, is how many 4-digit numbers can be made that have no repeats? So I need a 4-digit number, and it needs to not have any repeats, but that is the only stipulation, which means our first digit can be one of any digit, right? 0 through 9. So there's 10 options. And since I cannot have a repeat, this then goes to 9, and then down to 8, and then finally to 7. So to find the total number of 4-digit numbers that have no repeats, I can do 10 times 9 times 8 times 7. And that gives me 5,040. Now, without knowing it, we've actually just done a permutation. And we haven't really defined what a permutation is a whole lot yet. And so we're going to take a look at a couple other examples of permutations, how we can shortcut it a little bit, and then what it actually is. So here's an example of a permutation. Okay, so in baseball, most high school teams have between 15 and 17 players. So we're going to say there are 17 players on a baseball team. The coach has to select 9 players to make up the batting order or the lineup. So he chooses which 9 players are going to bat and what order they bat in. So he might say, I'm going to pick players 1, 2, 3, 4, 5, 6, 7, 8, and 9, and that might be the order in which they bat. Or he could go almost the exact same lineup, but switch the last 2 batters. Okay, and it's important to understand for this problem that these 2 lineups are considered different. If you've never played baseball before, you might not think it matters. But if you're someone who's played baseball, you understand that hitting 9th versus hitting 1st versus hitting 4th all have really different implications and kind of strategies behind them. So the order in which you line these people up does matter. So there's a ton of lineups I could make just with those 9 players, but there's actually 17 to choose from. So this number is going to be pretty big when we talk about how many different lineups could a baseball coach make. One way to do this, and this is where we're going to learn our first shortcut in this chapter, besides factorials, but it's kind of similar, is the coach is going to pick 9 players to bat. And he's then going to make a selection for who's batting first and then who's batting second and so on. So he has 17 options for the first batter and then 16 for the second batter, 15 for the third batter, so on and so on and so on, right? Down the line, and then we can multiply those all together. But there's a handy trick in most calculators, including the TI calculators that we use, that we can shortcut that a little bit quicker. Now, since the manager or the coach is choosing 9 players from a pool of 17, what we can do is in the calculator we can say, all right, from 17 you are going to pick 9 and arrange them in a certain order. So there's a button in the calculator that's labeled NPR. Okay. The N is how many people you are choosing from. So how many possible options do you have? R is the number of people that you are choosing, which in this case is 9. And the P means that we have a permutation on our hands, meaning there are no repeats and the order matters. So that's essentially what a permutation is. We're choosing things in which we can't repeat the same value, and the order does matter. So what we're going to do here is we're going to type this into the calculator, and to do that, we need to first type that N value, which is 17, then go into the math menu over to the probability part of it, the probability tab, and go down to this NPR. Okay, that is then put there. Your calculator might not like put the 17 as a subscript, like we saw last chapter with sequences, but that's fine. And then no matter what calculator it is, you just hit 9 and then hit enter. Okay. So the number of ways to choose 9 players from 17 total is 1, 2, 3, 8. What's that? 8,821,000,000, which is a crazy amount of lineups for just for a baseball team. So 88216 8821612,800. So there are 8,821,000,000. That's crazy. Again, like if you put an 18th player in the mix, now like that's just going to make the amount even more, like it gets out of control very quickly. But this is an example of what a permutation is and a situation in which we could use it. Okay. So again, permutation, there has to be no repeats, and it's important that order matters. Order matters. Meaning if you're batting first or if you're batting fifth, that is different to you. Okay, so another example, this would be how can we select 5 random letters from the alphabet without repeating? Well, if we're going to make, now you might say selecting 5 random letters doesn't really matter, but if I pick the first 5 letters and try to make a word with it, versus if I pick those same 5 letters but switch up the order, right? This is a different word. It's a different arrangement of letters. It looks different to us. So that means I can use a permutation for this problem instead of actually like hand calculating. This one wouldn't be terrible to type in the calculator, but of 26 letters in the alphabet, I'm going to pick 5 of them. Now you notice in the last problem I put NPR, right? I put the N before and the R after. Sometimes you'll see the N and the R written there. Other times, like you'll just go right to the numbers. So you'll often hear people refer to this as 26P5, and that P just means the permutation. So I'm going again in the calculator, type in 26, go to math, over to probability. The second option is the permutation, and I'm choosing 5 letters. Okay. What's kind of nice about this is that if I want to do the same thing, but let's say I mistyped and I want to do 4 letters instead, then I can just go here, change it to a 4, and then I get my new value. Okay. So this is allowing us to do these calculations without having to manually enter 26 times 25 times 24 times 23. That's not a terrible calculation to put in, but it does save us time in the long haul. So 789 3600 was our answer for this. Where did we go? So 789 3600, which means if you're selecting 5 letters from the alphabet with no repeats, you could have, in theory, 7.8 million different quote-unquote words. Okay. Now, again, that's with no repeats, and we know that words have repeats, but in this situation, that's the number of ways that you could pick 5 letters. That's the number of different sets you could have. So if we think about this, okay, you and 3 other finalists are up for 2 internship positions. This summer, how many different duos can be chosen for the positions? So 4 candidates, there's 2 spots. They're going to pick 2 people to be an intern. And so this doesn't work as well in a video. Like I have a smartboard for a reason with this problem, but we're just going to number these people 1, 2, 3, and 4. So obviously, one possibility is that 1 and 2 are chosen to be the interns. It could also be 1 and 3. It could be 1 and 4. I could also, so those are the only possibilities that have person number 1 chosen as part of it. Well, I could also do 2 with 1, 2 with 3, or 2 with 4. Okay. I keep this pattern going: 3 with 1, 3 with 2, 3 with 4, or finally person 4 and person 1, person 4 and person 2, or person 4 and person 3. So this gives me a total of 12 different combinations for that summer job. Now, this is where our EQ comes into today. Even though this looks like 12 different duos, the important part in this problem is that both people get the same result. Like both workers, if you get the call and say, hey, you're an intern, it doesn't matter whether you're the first one chosen or the second one chosen. Like the outcome is the same, right? You are an intern. It's not like you're the intern plus and the intern minus, right? They're calling two people and saying, hey, you have the internship. So what happens here is we've actually duplicated some duos. Like 1 and 2 is the same as 2 and 1, right? Like it's the same two people. So I don't need to double count that. So I'm actually going to cross off all of these duplicate duos. So 1 and 3 was already picked, so I don't need 3 and 1. 1 and 4 was already picked, so I don't need 4 and 1. Okay, 2 and 3, so don't need 3 and 2, and so on and so forth. Okay, so what ends up happening is I cross out exactly half of the duos because we've duplicated every one. So instead of 12 different combinations or 12 different pairings that could get that internship, we actually have 6. So this would be 6 different duos that could be chosen. And here are the 6. 1, 2, 3, 4, 5, and 6. Okay. And the key to this problem, right, and here's the deal, is if you were to take, I had 4 people and I'm picking 2 of them, so it must be a permutation, right? If I go to 4 math over probability, okay, that will give me 12. And again, it makes sense because the reason I'm getting an answer of 12 is that I'm like, this permutation is counting those duplicate pairs. So I can actually get rid of this. 12 is not the answer. The actual answer is 6. And that leads us to a combination in probability. Okay. A combination is the same in that you can't repeat, right? In the previous example, you couldn't call person 1 and then call person 1 again and be like, you got both internships, right? You can't repeat the same person, but the order in which you choose them does not matter because the results are the same. So the big thing when you think about a combination is that the order does not matter. The order in which you choose things doesn't matter. Here's another example. You have a coupon for a 3-topping pizza. You can choose from chicken, sausage, mushroom, or peppers. How many different pizzas can you order? Okay. Well, if you're a smart person, and that's kind of rude, but let's not say smart. If you have good taste in pizza, there's one answer here. It's a chicken, sausage, and pepper pizza. Mushrooms are gross. Don't eat mushrooms. Now, I could call your favorite pizza place and say, hey, I want a chicken, sausage, and pepper pizza. It is reasonable to state if I call an hour later and say, hey, I want a chicken, pepper, and sausage pizza, that is going to end up being the same pizza. The order in which I said the toppings was different, but it's not going to give a different result. So there's a bunch of different combinations here. I could say chicken, sausage, pepper. I could say sausage first and then chicken and peppers, or sausage, then peppers and chicken, right? I mean, I could do a lot of different things with this. I could also, instead of starting with sausage, I could say, hey, I'll take peppers, sausage, and chicken, or peppers, chicken, and sausage. There are 6 different ways to call and say the exact same thing, which is, I want these 3 toppings. So what we can do to get the answer quickly is to say, of 4 toppings, we are choosing, and order doesn't matter, 3 of them. Okay, so that button also is in the calculator. Now, because order doesn't matter here, this is going to cut down drastically on the number of possible pizzas. Okay, so if I can compare real quick, if I can compare 4 combination 3, which you just saw the answer was 4, to 4C, oh boy, that's the same thing. I can if I can compare that to 4 permutation 3, okay, so if it were a permutation, I would have 24 possibilities. If we're going to say that the order doesn't matter, that number is cut down to 4. And the reason why, and I don't want to get into this too much, if you look at the difference between 24 and 4, this permutation is 6 times more than the combination, and that's because each pizza can be represented in 6 different orders, right? I can order those 3 toppings 6 different ways, but it's not going to produce a different pizza. So in this, I mean, that's a long-winded way of saying this pizza is going to end up, or the number of pizzas I could order is only 4. Okay, that might seem a little crazy, and if you want to list them out, you can. Okay, but there are only 4 different pizzas I could order, and actually, I'll prove it to you in 30 seconds. Because basically, what you're doing is choosing what topping don't you want. Right, you're going to pick 3 toppings, and you're going to leave one off. So I could do chicken, sausage, and peppers, and leave off mushrooms. I could do chicken, sausage, and mushrooms, gross, and leave off peppers. I could do sausage, mushroom, and peppers, and leave off chicken, or chicken, mushroom, and peppers, and leave off sausage. Those are the only 4 options that you have. Those are the only 4 pizzas you can order, and it doesn't matter in which order you say them on the phone or type them into, the online ordering app. So let's think about this. At a speech competition of 6 students, the top 3 are going to move on to the next round. How many different sets of students can move on? So you are one of 6 competitors, and the top 3 move on to the next round. Based on just what's given, the fact that all 3 people are moving on to the next round, and there's no advantage to being first over being third, like you might say, oh, like I feel more confident if I'm picked first. But if you move on, like you're just excited to move on. So this is another example of a combination where if I say, hey, students 1, 2, and 3, you moved on. But if that announcer said it in a different order, you don't care, right? Like you're moving on. That's the same set of 3 students that are moving on. So this would be of 6, I am choosing 3 students. Now the C doesn't stand for choosing. The C stands for combination. But I just like to go 6C3. I think of it as you're choosing people to move on. So math over to probability. Out of 6, I'm choosing 3 to move on. So that means there are 20 different sets of students. And again, if you go 6P3 accidentally, this number is going to skyrocket because you can reorder these so many different ways. So I go from 20 to 120, again, off by a factor of 6. Okay, so in this case, there are 20 different sets. Biggest thing with this when you're counting is, does order matter? Okay, permutation means yes, order does matter. Combination means no, order does not matter. So, does the order you finish a race matter if medals are handed out? Well, if you're getting silver, bronze, or gold, yeah, that matters, right? Getting first place versus getting third place yields a different result. It's a gold medal versus a bronze medal. So here the order does matter, which means I have a permutation on my hands. There will be more possibilities for this. Does the order you finish a race matter if you're qualifying for the final? Let's say you qualify for the finals. Top 3 racers get to move on to the final heat. That doesn't matter. As long as you're top 3, you move on. So this would be an example of a combination. Again, we're not getting into true probability yet. We're just figuring out how can I count stuff. This is the most important slide. Does order matter? Yes or no? And what do you do in each situation? Okay. Last thing I will throw out, again, both of these, what they do have in common is that there are no repeats allowed. Okay. If there are repeats allowed, then the way you would count it doesn't fall under either one of these categories. Okay. So go ahead, try these 2, see what you can come up with. How many different groups of 8 can move on to the final heat of a competition if there are 16 competitors? Again, final heat of a competition, order does not matter. So out of 16, I am looking for a combination of 8 of them. So 16 math left, 3, 8. Whoops. 16 math. On your calculator, you probably only have to go left one time. I know some calculators, the probability menu is the last menu. But I digress. This video is getting ridiculous. 12,870. Okay. And how many ways can a president, vice president, and treasurer be chosen? Obviously, the order in that matters because you're assigning a different role to those people. So of 12, you are picking, again, the P doesn't mean picking, it means it's a permutation. But you have a permutation of 3 from 12. Math over 2. Oh, God. Math left 2. Boy, struggling. So out of 12, I want to pick 3. So there are 1,320 different 1,320 different trios, I guess, or cabinets, or however you want to think about it, that you can get from 12 people. Okay. And again, this is kind of what we were alluding to earlier. It's kind of just summarizes the whole thing, puts it all together. Permutation order matters. I'm going to slide this over just a little bit. In a permutation, order matters. In a combination, order does not matter, but the N and the R mean the same thing. The first value is the number of items to choose from, like how many options do you have, and the R is how many items are you choosing, which from 11.1.1 would be how many slots are you filling. So how many lines did you write down? That's your R value. And then how many total options do you have? That's your N value. So that's going to wrap up 11.1.2. Again, got a little long-winded, and I apologize for that. But this lesson is super important that we can find that difference.